Hope my voice is audible. So we have started the stream at 11:30 in the morning, and I want to complete the trees today because I have already seen some AVL trees. I mean, with a few minutes or hours of revision, I can code AVL trees, but I have not started the trees. So today, this session is going to be a tough session in my opinion because we are supposed to do how Beatrice insertion and deletion works in a single piece of code. And Beatrice is not a simple one, but we are not weak either. So I'm completely new to Beatrice. I should be able to implement them in this session. Alright, the homework and more importantly, explain everything more. Please. So there is something called okay, a lot of philosophy is going in my mind right now. You can only be good at very few things. Please 11th. We will have a bigger session. There is something called okay, a lot of philosophy is going in my mind. Okay, why am I speaking like that? The tree printf scanf, okay, and you need malloc and free functions. For that you need the standard library. Standard goal is to get a boolean function, a b-tree node. It is a dynamic array of keys in this node, a dynamic array of child pointers, okay, and the current number of keys, and true if node is leaf. Minimum degree defines a range for number of keys. B-tree node, create a B-tree node. T is equals to minimum degree. If is equals to whether this node is a leaf or not. B-tree create node. So a structure defines attributes, all the attributes. So it is having T and it is having a leaf. So it builds from bottom up. So you are allocating memory to the node structure. And if it is not a node, I mean, check allocation success. Memory allocation failed, okay, exit failure. This is just an edge case. I mean, the case if memory is not allocated, let's leave it. Node of T is equal to T. Set minimum degree. Node of leaf is equals to leaf. Okay. Node of N is equals to 0. So a leaf is a boolean value. Initially don't have any keys. That's true. Node of keys. Keys are I can hold up to. Okay, you are allocating memory to this dynamic array. Okay. Int malloc size of int 2 times t minus 1. Okay. It node of say children array can hold up to 2 times t child pointers. Okay. So let's get with the analysis of this code. How big is this code? Yep, this code is pretty big. Yeah, there is no deletion. Six cases. Wait, do we have B-tree deletion in the syllabus? The level they're assuming for an engineer is really high. Wow. Wow, just wow, man. There is deletion as well. Nah, why are we even worrying about that? Insert insert normal split child search traverse create node. We trace. So the first step is create a structure. Keys. It is a dynamic array, right? And it will have T, the order, and it will have leaf, a flag, boolean, or a leaf will have C for child and for current number of things. It is having five attributes. C for child pointers. So Okay, gives you a dynamic array when using looking tree means on dynamic array and another first like pointers. Is a pointer to an integer or more practically can point to the first element of an integer or declares a pointer variable that can hold address of an integer or an array of integers. Okay, you can create the dynamic array allocating memory. C is a pointer to a pointer to a B-tree node or in simple terms, it is a dynamic array of pointers to child nodes. Pointer to a pointer. Nice. So what I have has to perhaps pointer to a pointer. Okay, nice. These are pointer arrays, and C is pointing to these pointer arrays, and these pointer arrays are pointing to the childs. That makes sense. Okay, nobody's here to listen that. Okay, okay, okay. So we have declared a structure of B-tree node. So it will have keys, and it will have childs, and it will have T, and it will have N, it will have leaf. Nice, nice, nice. And create node, you are allocating memory to the structure, and you are taking the order, and if it is a leaf or not. Node of leaf is equals to leaf. It is just a boolean, and we have three integers and a boolean and a structure and the B-tree node. You are allocating memory 2t minus 1k. Okay. Well, our B-tree node size now. Uh, I mean, your brain is not going to explode anytime soon, so let's just have this number writing Australia without hands. Type dev struct B-tree node. In case it is having base and it is having order and B-tree node pointer to the childs and the level, and if it is boolean leaf or not. and the number of actual field is that is called as the trainable. What the heck, man? So how does a type abstract? What are the alias? Type, uh, we, not writing this one again, man. So what does it have? It have keys and it will have string. We train on pointer to a pointer of child nodes and it will have an int and the number of article keys and it will have the orders or order and it will have boolean link. You can call this as pre node, right? And now so pre node create. It will take two values. It will take the order and it will take the relief. Right. So P three normal new normal is equals to P three normal star of ML of size of P three node. You have allocated that. So let's say the allocation. Yes, the allocation is working fine. Nice. Now what you need to do is you need to allocate memory to the keys. Wow, this will take almost 3 to 4 hours to learn if I'm not wrong. If we go in this phase, I mean, I do not have anything more important than this going on. Okay, you will put the T and you will put the leaf and you will initially set the number of keys to 0. Okay, you can work from here on. Okay, so we have understood the structure. Then what are we doing is allocate memory to B-tree node and new node of T equals to T, new node of and no, leave is equals to leave, right? And then new node of keys is equals to the data type int star of malloc 2 times t minus 1 times the size of int, and then you need to allocate the memory to the child. Can we just try to see? Yeah. So what type is it? It is a B-tree node type, double pointer envelope, right? 2 times t times size of and this 2 times t times size of B-tree. Let it be. That's it. B-tree node star. That's it. And you are allocating that to 0. You are initialize the child pointers to 0. Okay, so where are we? We have allocated memory to the B-tree node and calling it new node of t is equals to t, new node of leaf is equals to leaf. And now you are allocating the memory to this new node of case. Since it is a dynamic array, int star of malloc 2 times t minus 1, right? 2 times t minus 1 times size of int, right? And now you are getting the c is equals to retrain of double star in malloc 2 times t times size of retrain of star, because it is a double pointer. You have allocated memory to all of these things, and now you need to initialize them to 0. For I is equals to 0, I less than 2 times 10, I plus, right, we will number. See, and what is happening here? Allocating them to 0. Yeah, because it is a time measurement can take. We see implies a customer return what are you returning? Mm, so, uh, like, get a T and then get it. 1, 2, 3, and 4. You forgot the N. No, that's it. The initialization, sorry, not initialization, the declaration and memory allocation itself is taking like 23 lines of code. Wow. We have done until here. And B tree traverse, so we are starting at the root. If root is null, there is nothing to do. Okay. Well, I less than root of n for each key before printing keys of I traverse the child C of I. If not equals to root of leaf, there is no root of leaf. B tree traverse root of C of I. That is recursive case. What is the base case? 500 transactions. Information open. Wait, root of C. Okay. We got a traversal function, we got a search function, we got a split child function, the important function, and inserting the non-full function, and finally the insert function, and the free function, and the main function that is entirely about insertion. And deletion in B-tree is kind of complex if you ask me. Okay, people, that is cool. Oh, we are making progress, even though if it is slow, it is a steady progress. I think we will sit here for 3 more hours for understanding this. That's it. So, traversing. Traverse, it is a recursive function. Is it void traverse or B-tree traverse? You can write a void function for traversing. Yep, we have it. Okay, that is the base case. If root is equals to none, return. Even a void can have a return, that's not the value. Any function can use the return keyword. If n I is equal to 0, if not root of wave. How many times should it be iterating? Root of n times. Corruption. My writing on this graphic tablet is becoming improved day by day. If not root of leaf, that means it is not a leaf node. What will you do if it is not a leaf node? Recursive call traverse node. From where the heck did he get the root? I have been writing root for this long, but didn't realize from where I got the root. Okay, we will go down and I will print the root of p sub pi. You will print the elements of the dynamic array set. Finally, traverse the last shape, if not root of leaf. One more time outside. To traverse the last chunk. Okay, that is all about the traverse function. You just wrote everywhere. Oh my god. Yeah, no one's here, as usual. Okay, this is all some stuff. Oh, let it be. Oh, traverse, battery node, root. It will take root as a parameter. And what will we do? What will we do first if root is equals to null? Return. If that's not the case, um, for here it is a recursive function I is equal to 0, I less than root of n. You are traversing n times I plus plus. because n defines the number of keys, right? If not a not a deep node, if not a deep node, then what are you going to do? Then you are going to traverse the root of C 5. You will traverse the child node and after traversing the child node, you will write what to do. Percentile backslash t root of keys of I. You will print out of the case and then so traversing is not a way first with the traversing different languages. Okay. If not equals to root of the tolerance root of say of like numbers and a function statement. That's also idiomatically is don't confuse me now. Create and travels. We have created, we have traversed, and we are supposed to search that now. So empty tree, okay. If I is less than root of n, then k is greater than root of k. So okay, that is the key that we are taking. K is greater than root of k. Hmm. Okay, this is searching. This is rich. Insert now. Developer function. We have a bit of a structure. Oh, oh my god. Hello. So yeah, I was too tired and it was seeming like something's wrong with me. But that's not the case. My brain is too tired after reading all of this code. That's it. Mm, so Beatrix, I need a small break. Um, so let us have a tree. Okay, so here the elements are placed in ascending order. Let's say the key to be found is 150. Here, elements lesser than 100 will be inserted, and here elements that are between 100 and 200 will be inserted. Something like that. Here, 200 to 300 will be inserted. Here, greater than 300 will be inserted. I'm not saying this is the exact B tree, but this is how the structure of B tree works. So, if you need to search for an element, so yeah, if not root, just return. This is a null case. Mm, right, if there is no root, then you are just going to return. So you are going to iterate until while you will initialize int I before and while I is uh, while I is less than n, because at max you need to iterate that for n times, and keys of I, keys of I is less than key. Is that the case? Yes, sir. So still all right and bullish, okay. Just don't want it to be placed here. So keys of I is less than key. That means we don't need to search this 200, right? We can, at most, we can search until here because we are sure that after this there is no element to be searched for. So you can increment the value of I. So does it place to anyone like int I is equal to 0? By updating initially, I need to ask this question. If I is less than n and piece of I right, and keys of I is equals to k, you will return the root. If root of leaf, it means if it is a leaf node, then you will return. What will you return? You will return none. Which is not necessary actually. All right, we are not doing searching now. We just wrote to create functions and traversing function. We will get forward with the standards. So means we can hold at most 2 by 1 sound. understanding, but a lot of less doing. So we are creating a new node with the T and with the leaf. So what is Y? Y is a leaf node here. Sx is a parent node and Y is a leaf node. We are creating another node Z. So let's say this is a parent node and this is a child node. You need to split this node and send this to parent. For this, you are creating another node Z that is identical to this Y node. Right, copy last t minus 1 piece. Okay, Z node will have the first t minus 1 piece. So for I is equal to 0, I less than y of t minus 1. Y of t minus 1, I plus plus. Ah man, we have a good video on YouTube that is showing the B-tree implementation. Yeah, I might get a copyright strike for browsing the internet like this. We don't have that gel land by myself. This might be really helpful. We are creating a new node and how many keys, how many number of nodes will it hold? T minus 1 piece, okay. Oh god, that is like a temp. But the thing is you do not have a temp. Because this is not a primitive data type. Okay, last T minus 1 piece from my to Z. Z of keys and Z. Y Z of piece of J is equal to Y of piece of J plus Y of T. Okay. Copy child pointer if y is not a leaf. If y is not a leaf, okay, you are copying the child pointers. Reduce number of keys in y. Okay, shift children right. Hmm. So I will come back.